In this short video, we're going to go over some of the basics of analytical methods. So for any method of measurement, this could be absorbance, it could be HPLC, it could be anything really, there are several key statistics for you to understand that affect your results. And these include the limit of detection, LOD, limit of quantification, LOQ, the accuracy, the precision, and the linear range. So limit of detection, simply put, is the level of output from your assay that is statistically different from the background or the blank. So how you calculate that is you run a blank several times to get a distribution, and you would have an error. So this would be 3 standard deviations from the blank, so this would be 1 standard deviation. Right, so you have this distribution that's defined by the blank or water or whatever your empty control is. And the level at which you can say that you statistically are confident that you have actual analyte in your sample would be when you're statistically different from this, which is 3 times the standard deviation of the blank. At the 3 LOD, or 3 standard deviation, defining the LOD as a 3 standard deviation, you have a very small chance of having a alpha error. So if you actually have analyte, you will detect it, right? It's a very small chance that you would have that error, 1% at 3 times the standard deviation. However, the beta error, the probability of false negative, is 50%, meaning you may actually have sample, but you'll say that you don't, right? And so for this reason, although we can be sure if you have a signal that's real, that you actually do have something in your sample, it's not really a good range to be quantifying your analyte. And for that, you really need to be at the limit of quantification. The limit of quantification is the lowest concentration level at which you can definitively say or estimate the actual concentration of the analyte in your sample, right? And this would be 10 times the standard deviation of the blank, right? It could be any x, but we're going to define it as 10 times the standard deviation. And at this level, your distributions are no longer overlapping at all. So you're beyond statistical significance, and you're at the point where your chance of a false negative is very, very low. And in this range, you can start to actually put a number to the amount of analyte you have. And importantly, the limit of quantification and the limit of detection are both determined by your blank. Right? They're not determined by these distributions, but by the blank distribution, because you're making a comparison to a control. For all methods, you will also have a term which is accuracy, and you'll also have precision, right? So accuracy would be how close you are to the real value, right? So you can have an accurate method that's got a lot of noise, so it has a high standard deviation, or you can have an accurate method that has a low standard deviation. Accuracy is how close you are to the actual value. So if you actually have if the real number is 1 gram per liter and you're measuring 1 gram per liter, that would be an accurate method. A precise method really dictates the standard deviation of the method, meaning how tight your samples will be if you run the same sample over and over and over again. The standard deviation will be very small. That means the method is very precise, right? So you can have a very precise method that's accurate, but you can also have a very precise method that's not accurate. So you would have 1 gram per liter actual value. I mean, you may be reading or getting an output of 0.5 gram per liter, for example. You really would like your method to be both precise and accurate, but depending on the use, you can have trade-offs. You also need to understand what the linear range of your assay is. You only want to be giving a number to your analyte or quantifying your analyte in the linear range. So if you have some response, this could be absorbance, it could be fluorescence, it could be the peak area on an HPLC, and you have an amount of analyte. As you increase the amount of analyte, you'll be able to tell a difference from the blank, which is the LOD, so that's the statistical difference. LOQ is then when you're completely, your chance of a beta error is very low. And then you from this limit of quantification up until you start to saturate the detector or saturate the response, you have a linear range, right? And the slope is equal to the sensitivity. And so you really only want to be quantifying in this range. If you go into this range, you may have a curve that slopes back down or goes up. Could do lots of different things. And particularly if it went down, you could imagine that if you have this reading, you're going to say it's this analyte concentration, but it's actually a lot more, right? So you want to really be careful about the linear range of your assay and only be quantifying things in the linear range of your assay. You also need to sometimes take into account that your standard curve may not be the same as your sample. And this happens particularly in bioprocessing or fermentation because you may have a media, for example, where you can put your standard in, but the media will change over time because other things in the fermentation are being produced, things are being consumed, there's other molecules being made. So there can be things in the matrix. The matrix is that what the sample is in, what the analyte is in the sample, that affect the reading, right? There could be things that coalute with your product or your analyte of interest. And so we really need to do things like that are spike recovery experiments, which allow us to compare the calculated analyte in a sample matrix versus the calculated analyte in a standard curve. Right? So we spike the standard or the analyte into the matrix of interest, and we try to see what reading we get back out. Right, and you want to be, this would ideally be as close to 100 as possible, 100%, so 1, where you have a really good reading between your matrix and your standard curve, indicating that your matrix is not impacting the analytical method. If this number is too far away from 1, then it suggests that you need to redevelop your method, or you need to dilute your samples to dilute out the matrix effect. Importantly, in most analytical methods, we use the term RSD, or relative standard deviation. And this is because the absolute error will change as a function of the concentration of the analyte. Meaning if you have a 1 gram per liter sample, you may have plus or minus 0.05 gram per liter, which would be a 5% relative standard deviation or relative error, right? But you wouldn't expect that absolute error of 0.05 gram per liter to hold if you were to have a 100 gram per liter analyte, right? If you had a 100 gram per liter analyte, that'd be a very small error to have only a 0.05 gram per liter error. And more likely you'll have a 5 gram per liter error, which would be a 5% of the 100 gram per liter. So in general, we expect that the error will scale with the absolute amount of analyte that you have in your sample. So this is some of the basic terminology for analytical methods that you'll be using in the labs and throughout this course.